Hello and welcome to our lesson on techniques for finding derivatives. So far we have talked about a derivative in terms of the definition of a derivative, or finding that derivative in terms of the definition. So we said if we're given a function, let's just call it f of x, that its derivative is defined as the limit as h approaches 0 of the difference quotient, and we would call that f prime of x. So we would say its derivative, f prime of x, again, is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. And when we're finding that limit as h approaches 0 of that difference quotient, when we're finding that derivative, we are finding an equation or a formula that allows us to find an instant rate of change, or an instantaneous rate of change, or a slope at any point on a given curve. So it's giving us an equation or a formula, and if we input a specific x value into that equation or into that formula, then we find the instantaneous rate of change or the slope of that function at that particular x value. So again, this is a definition that we use to find the slope at any given x value or at any given point along a curve. Okay? So we spent some time working on the difference quotient, finding the limit as h approaches 0 of that difference quotient to find those derivatives. And what we're going to do today is talk about some shortcuts. Basically, that's what they boil down to. And the shortcuts come from just repeated use of this definition to find derivatives. We end up seeing the same things occur over and over. And so those shortcuts are going to simplify our work tremendously. Now, before we get into those shortcuts, those derivative rules that we're going to discuss, I want to show you some other notations for derivatives. So f prime of x is just one notation that we can use for a derivative. I like this one, but there are others you need to see. That way, when they pop up, you're not like, what is this thing talking about? Okay? So f prime of x, again, this would be the derivative of our function if it's called f of x. We can also call the derivative of y with respect to x that derivative using this notation. So dy dx is how we would read that, but it is the derivative of y with respect to x. Okay, or we have d dx of f of x, that is the derivative with respect to x of our function f of x. And then these two are kind of read and said the same way, but the derivative of x derivative of x of f of x. Yeah, that's the derivative with respect to x of f of x. I think I said that wrong. But yeah, different notations that all mean the same thing. Take the derivative of the function, find the instantaneous rate of change or the slope at any given point on a curve. So these are four different notations that we could see to find the derivative, and you'll get used to seeing each of them. This happens to be my favorite, the prime notation, but I also use this one quite a bit, but so you're familiar. Okay? So the derivative rules, again, these are established by patterns that are developed in just repeated use of the definition. So if we were to use this limit definition just over and over and over with a linear function, we would see that our slope is the same every time. If we did it with a quadratic function, again, we would see some patterns, cubic function patterns, square root function, whatever the function is. If we can find its derivative, there would be some patterns that would shortcut the process so that we wouldn't have to use that definition to find our derivative. So patterns developed in the repeated use of the definition to find derivatives, they help us shortcut the process. And I know that sounds great, because who wants to do that difference quotient over and over and over? And honestly, even for a relatively simple function like x squared, finding the difference quotient is kind of tedious. So just keep in mind that we're going to use these shortcuts to find our derivatives. It will make the work much faster. So the process is simplified, but the interpretation of the derivative isn't any different. So even though we're going to do a different, or work on a different process to find the derivative, we are still finding slope, we are still finding instantaneous rate of change. We are still looking for the slope of a tangent line at any point on a curve. So, first let's talk about probably the easiest of the rules. We call this the constant rule, and it should make perfect sense. If we are looking at a constant function would be, you have a function like y equals just a constant, like 5. Anywhere on that horizontal line, our tangent would be also a horizontal line. So if the slope of our tangent is horizontal, that means our slope is going to be 0. So the derivative of a constant is going to be 0 because the slope of any tangent line on a constant is 0. So that's what the constant rule says, that the slope of any tangent line to a constant function is going to be 0, which means the derivative of a constant is always 0. So there's the sort of informal explanation. Here's formally how we would read this. If our function is a constant, that's all it says. If f of x equals c, where c is just some real number, it's just a constant, then the derivative, f prime of x, or the derivative with respect to x of that constant, will always be equal to 0. So if I asked you to find f prime of x, given f of x is 7, you have to recognize this is a constant, and so f prime of x will be 0. The derivative of a constant is 0 because a constant is horizontal, so the slope of any tangent line to that horizontal has to be 0. And different notation here, but the same concept. If I asked you for the derivative of y with respect to x, given y equals 2, recognize again, that's a constant. So we would say the derivative of y with respect to x using this notation would be 0. And and then here, it's the derivative with respect to x of -4. So again, this is a constant. We're going to say the derivative with respect to x of this constant, again, has to be 0. Okay, so derivative of a constant is 0. That's a pretty easy one. Let's talk about the next one, which is probably one of my favorites and probably one of the most commonly used derivative rules. So this is called the power rule. The power rule applies when we're taking the derivative of something like x to the nth power. So the derivative of a function, really it's like a polynomial function, so x to the nth power, some polynomial function basically, is found by doing two things. You multiply, so it's found by multiplying by the exponent, and then decreasing the exponent on x by 1. So two things are going to happen. Whatever our x is, we're going to multiply that x by our exponent, and then we're going to decrease our exponent by 1. So that's the informal take there. Here's formally what we're saying. Again, if we have some function where it's x raised to the nth power, and n is just some real number exponent. So your exponent is, again, any real number. The derivative, f prime of x, or the derivative with respect to x of that polynomial term there, is found by multiplying x by the exponent. So you see a coefficient of n here. And then decreasing our exponent by 1. So whatever the exponent is in our derivative, it's 1 less. Okay? So for example, here, if f of x is x squared, and I said to find f prime of x, again, I no longer have to use the limit as h approaches 0 of the difference quotient to figure this out. Our power rule says multiply by our exponent and then decrease our exponent by 1. So by looking at this, I know f prime of x is going to be equal to 2 times x, again, because this gets multiplied here. And then decreasing this by 1 means it's going to be 2x to the first. So our derivative is 2x. Instead of all of that work, there it is, we're done. Okay? Or similarly here, if y equals x cubed, and I said find the derivative of y with respect to x, then I would say dy dx, derivative of y with respect to x, is going to be equal to multiply here, so that's going to be 3x, and then reduce this by 1, so it's 3x squared. And then here again, different notation, the derivative with respect to x of x to the 4th power. So we're going to say the derivative with respect to x of x to the 4th power is going to equal, again, multiply, so that's going to be a 4 in front of my x, and then reduce this by 1, so 4x cubed. So simple. And just imagine, so we did the limit as h approaches 0 of the difference quotient of x squared. When we do that, instead of an x squared in there, we have an x plus h squared, and then minus our x squared, and then divided by h. It's really not terrible, but it's work. Imagine if this was to the 4th power. Unless you know binomial expansion shortcuts, that becomes such a pain to have to expand. So this power rule really saves us some time. Okay, so that's our power rule. We're going to multiply by our exponent, decrease our exponent by 1. Now sometimes we have a function that's being multiplied by a constant, so we can apply this constant multiple rule that says the derivative of a constant multiplied by a function, so times a function, is just the constant times the derivative of the function. So informally and more formally, again, if we have some function that's being multiplied by a constant, what this says is we're going to take the derivative of that function and then multiply the derivative by the constant. That's our derivative. So whether we're multiplying the function by the constant, we can separate that constant out, take the derivative of our function, and then bring that constant back in. So hopefully that makes a little bit of sense. This is all just fancy notation, assuming the derivative of our function exists. So the derivative of our function with respect to x, again, if it's some function multiplied by a constant, we'll just take the derivative of that function and then multiply by that constant. It's like we can factor it out and then multiply it back in, or take our derivative and then just multiply by whatever that constant is. So again, if we look at this example, so if I have f of x equal to 3x squared and I wanted to find f prime of x, this would be like 3 multiplied by x squared, right? This is a constant times our function. So this is saying take the derivative of the function and then go ahead and multiply by the constant. So the derivative of x squared, we just saw that one. We'd multiply by 2 and then decrease the exponent by 1, and then we're saying just take that and multiply by 3. So we end up with 6x to the first. Now, in this particular case, I probably wouldn't go through all that work, because we can just apply our power rule. If we multiply, instead of multiplying by 1, we're going to multiply by 3. So we're going to say f prime of x is 6 times x to the first power. So we're still going to multiply our exponent by that coefficient of 3 now, and then reduce our exponent by 1. So 6x to the first. Okay, and I was trying to delete this. So sorry. Okay, but again, if we wanted 3 times the derivative of x squared would be 2x, and so again, f prime of x, our derivative, is going to be 6x. Alright, not so bad. Now here, I just want to show you some other things that you can encounter. If we have a polynomial function where we can apply our power rule, that's going to be best case scenario. Now if we have a radical, I'm hoping you remember from college algebra that a radical can be rewritten with an exponent, and a rational exponent to be exact. So we had this property, again this hopefully looks familiar from college algebra, that says if we have something like the nth power of the nth root, of a to the mth power, that is equivalent to a to the mnth power. So you can rewrite a radical in rational exponential form by dividing the power by the index. So the power on the radicand divided by the index of the radical. So if you had, for instance, actually let me move this up here. If you had, for instance, something like the let's just say the cube root of x to the second power, that is the same thing as x to the 2/3 power. So the ability to take a radical and rewrite it with the rational exponent gives us something that now we can apply our power rule to if we're differentiating. So for example here, I would start by rewriting this function. So y would be equal to 2 times, this is an index of 2 because it's a square root, there's a power of 1 when we don't see it. So we're going to rewrite the square root as x to the 1/2 power. And now I have again a constant times my function. So I'm going to take the derivative of my function and then multiply it by this constant. So we're going to say the derivative of y with respect to x is going to be equal to 2 times, here I'm taking the derivative, so multiply by the exponent, and then decrease the exponent by 1. So 1/2 minus 1, well, that's 1/2 minus 2 over 2. That's going to be a negative 1/2. So 1/2 minus 1 makes our new exponent a negative 1/2. Okay, so the derivative of x to the 1/2 is 1/2 x to the negative 1/2. That has to be multiplied by the constant of 2. So 2 gets multiplied here. And then we have dy dx equal to 1 x to the negative 1/2. Now another rule I'm hoping you remember. We don't typically leave terms with negative exponents. It's not wrong, it's just a little more proper to have positive exponents. So when we see those negative exponents, I'm hoping we remember what to do with them. And so let me give you another rule from college algebra that I'm hoping you remember. If you have something to a negative power, it just means the base of that power is on the wrong side of the fraction. So a to the negative nth, for instance, would be 1 over a to the positive nth, and vice versa. So if you had like a to the negative nth on the bottom of the fraction, then you would move that to the top of the fraction to make it positive. So if you have a base with a negative power, it just means that base is on the wrong side of the fraction. So if it's on the top of the fraction, move it to the bottom to make the exponent positive, or vice versa. So right now this is on the top of the fraction because I could put a 1 under it and you could see that there. So if I was to make this more proper, it would be 1 over x to the positive 1/2. And that would be a perfectly acceptable answer. But because we started out with a radical here, it might be better to put it in radical form, although I'd take either one. So we can give this as the answer, that would be totally fine, or we could say 1 over the square root of x as our answer, and now that looks like a giant fraction. So we could also give this as an answer. Either one of those would be perfectly acceptable, okay? So hopefully I didn't make too big of a mess of that. Let's try one more. So let's find the derivative with respect to x of 5 over 2x cubed. So I would start this one in a similar way. I would probably simplify our original function first. This thing on the bottom being cubed, 2x times 2x times 2x means 2 has to be cubed, x has to be cubed. So 2 cubed is going to make 8, and x cubed would obviously make an x cubed. So we're really trying to find the derivative with respect to x of 5 over 8x cubed. And so I could apply my power rule. I want that x to be on the top of the fraction. So I'm going to use my negative rule in reverse. If I want to move a base, a power, or a base and its power to the opposite side of the fraction, I'm going to change the sign of my exponent. So I'm going to really try to find here the derivative with respect to x of 5/8 x to the negative 3. Now x is technically belonging to the top of the fraction, but then I can look at the 5/8 as a constant being multiplied by this function. Okay, so this derivative with respect to x is going to equal 5/8 times, take my constant and multiply it by the derivative of x to the negative 3rd. So I multiply by the exponent and then reduce the exponent by 1. So negative 3 minus 1 becomes a negative 4. And so we end up with 5/8 times negative 3x to the negative 4th. I can now multiply 5/8 and negative 3. That makes negative 15/8. And then I still have this x to the negative 4. And that would be an acceptable answer, but again, generally we want our exponents to be positive, so I'm going to put x back to the bottom of the fraction where it belongs. So negative 15 over x to the positive 4. Oops, there should be an 8 with that. And that would be, and I put the negative on the top, although it doesn't matter. So I'm going to clean that up and put it out there. There you go. That would be the derivative with respect to x of 5 over 2x cubed. Okay, and I promise much faster than having to use our limit definition. Alright, hopefully we're doing okay. Let's flip the page here. Another one of my favorite rules, simplifies our lives quite a bit, is if we're looking at the sum or difference of multiple functions. If we're taking the derivative of a sum or difference of functions, it's going to be equal to the sum or difference of the individual derivatives. So if we have multiple terms in a function, we can just take the derivative. Multiple terms meaning we have functions that are, or terms separated by pluses or minuses, hence sum or difference here, right? Take the derivative of each of the terms separately, and we get our collective derivative. So that's informally how we're looking at it. Here's what the formal piece looks like. Looks like a big mess. So again, we have some function that is defined as the sum or difference of multiple functions. So it's something like this, where you have an x cubed minus a 5x and then plus a 2. That's 3 different functions there. What this is saying is, when we differentiate, we just find the derivative of each of those pieces. Okay, and then we're adding or subtracting whatever the original operation was, assuming that each of those derivatives exists. So for instance, here, if we were using our limit definition, this would be a real pain, but because we have this rule, this shortcut, again, this is purely based on repeated use of the definition, this becomes really simple. So f prime of x, our derivative, is going to be equal to, we take the derivative here, so we multiply by 4, subtract 1 from the exponent, so 4x cubed. Take the derivative here, so we're going to multiply by 2 to get negative 6, decrease the exponent by 1, so we get a 1. And then the derivative for a constant is just 0. So I don't even need that plus 0. There's my derivative. So simple. Okay. Now remember, we can do other things with derivatives. When we're just finding the derivative, we're looking for a formula to get the slope at any point on the curve. But sometimes we actually want the slope of that tangent line at a specific point. So after we get the formula, we want to plug that x value in, and that's what we're going to do in the next example. So find the slope of the tangent line, which means find a derivative at a specific x value. So after we find the derivative, let's plug that x value in. So again, we're going to start by finding f prime of x, the derivative, super simple. Power rule here, so that becomes 3x squared. And then power rule here, technically, multiply, so we get a negative 5 in front, and then if we reduce the exponent by 1, we get x to the 0 power. Well, anything to the power of 0 is 1, so we're going to end up with just a 5 there, right? X to the power of 0, or anything to the power of 0, is going to be 1. And so this is just going to be negative 5 times 1, which is negative 5. And it should make sense that our slope is going to be negative 5 here, because that function is linear, and the slope for a line never changes. It's always the multiple in front of the x. Okay, so that's going to be a negative 5. And then I know the derivative for our constant is going to be 0. So our derivative formula is 3x squared minus 5. I could use that to find the slope at any point. Well, this is saying find the slope at x equals 1. So that means I want to find f prime of 1. That's going to give me that slope. So that slope is f prime of 1, which would be 3 times 1 squared minus 5. 1 squared is 1, 1 times 3 is 3, and 3 minus 5 is going to give me a slope of negative 2. So that would be the slope of my tangent line to this curve at x equals 1. And again, just because it's good to review, we can do multiple things here. We can find the equation, find the derivatives, find the equation to find slope. We can then actually find slope at a specific point, and then we can write the whole equation for the tangent line by finding the slope, or finding the derivative, and then finding the derivative at a location, and then using the point that we're looking at to write an equation for that tangent line. So this is like taking it to the next step. So if I want to find the equation for the tangent line to this function, I want to find the derivative first. So let me find f prime of x. So power rule here, 4 times the negative 1/2. Negative 1/2 times 4 would be a negative 2 for my new coefficient. Reduce the exponent by 1. So 4 minus 1 makes 3, so negative 2x cubed. Same thing here, multiply and then take 1 away. So 3 times 3 is going to be 9, and then we're going to have an x squared. And then the derivative here is just going to be 2. So technically we would multiply, we would get a negative 2, and then we end up with x to the 0, but that becomes a 1. So this is linear, that's going to be our slope. So minus 2. So there's our equation for our derivative. Now we want to know what's happening at x equals 1. So let me find my slope, which is my derivative at 1. So negative, oh, it's at negative 1. Almost messed that up. Negative 2 times negative 1 cubed plus 9 times negative 1 squared, and then minus 2. So we have, let's see, negative 1 cubed is going to be negative 1, times the negative 2 makes a positive 2. Negative 1 squared is 1. 1 times 9 is going to be 9. And then we still have a minus 2 at the end, so we're going to end up with a slope of 9. Now when we write our equation, remember our equation, we're going to start with point slope form, so y minus y1 equals m times x minus x1, and then we're going to simplify that down to our slope intercept form, which is just our y equals mx plus b. Okay, so here we have our m, we have our x1, we have our y1, so we're going to say y minus y1, so minus a negative 3 halves will be plus 3 halves. That's going to equal m, which we just found was 9. So here's m. And then it's going to be multiplied by x minus x1, so minus a negative 1 will be plus 1, and then we'll simplify. So we have y plus 3 halves equal to 9x plus 9. And then the last step here would be to just subtract this 3 halves over. So we're looking at y equal to a 9x and then 9 minus 3 halves. Let's see. I'm going to do the side work over here. If I have 9 over 1, and I want to subtract 3 over 2, got to get my common denominator, so it's really 18 halves minus 3 halves, which is going to make 15 halves. And if you don't want to do that work by hand, obviously you have a calculator. So if you had 9 and you wanted to subtract 3 halves, it gives you the decimal, which you could hit the little fraction button in the blue here. So I just, oops, right there, that little button. Just push that and it'll go back and forth from a fraction to a decimal. So 15 halves, I prefer the fractions, is going to be our final y-intercept. That's technically the y-intercept for that tangent line. So there it is. Okay, that's the equation for the line that is tangent to that curve at that point. Now the nice thing about this one is it's really easy for me to visually check my work because I have a calculator. So I'm going to do that. Take a moment to pause and show you how you can also check your work. And we did this before, but just so you can see it again. So I'm going to graph my function. I'm lazy to put f of x in there, so I'm going to call this y, although it doesn't matter. Let's see. We have a negative 1/2 x to the 4th power. And then we're going to add on 3 x to the 3rd power minus 2x. So there's our function. Now what we're saying is at the point which was given to us, negative 1 and negative 3 halves, which now it plots that point. At that point, the line that I have written there in pink should be tangent. So that should be the tangent line. So now I'm going to type that tangent line in there. Y equals 9x plus 15 halves. And perfect. Looks exactly how I would expect it to look. All right, I can see that line that I got there being tangent to that curve at that point. And you can zoom out a little so you can see it better. But that's exactly what we would expect to see. Okay? So a good way for you to check your work. Alright, so now that we've got some of that out of the way, and we will continue to work on derivatives, there's going to be more rules we'll put into place, and we'll get plenty of practice with this, but I want to introduce some of the places we can apply some of this, and we'll continue to work on the applications as well as we move through, but marginal analysis is one of the ways we can apply derivatives in business and economics. And sometimes this brief calculus class is called business calculus because there are lots of applications for derivatives in that realm. So in business and economics, when we're referring to rates of change, we use the word marginal. Okay, so rates of change as variables such as let's see, costs and revenues and profits. These are all things that are important in business and economics. All right, so we use the word marginal when we were referring to, or I should say they, I'm not really in business or economics, okay? But they use the word marginal to refer to rates of change. So when you see or are asked to find a marginal cost or a marginal revenue or a marginal profit, you are trying to find a rate of change for that cost or a rate of change for that revenue or a rate of change for that profit. So derivatives give us rates of change. So if I want to find a marginal cost, I find the derivative of a cost function. If I want to find a marginal profit, I find the derivative of a profit function. Okay, so since derivatives give us rates of change, since the derivative of a function gives us the rate of change of a function, we can find the derivative of cost, revenue, or profit functions to find marginal cost, revenue, or profits. Okay? Another thing that we consider often in business or economics is demand. And you've probably heard of demand before, but we can actually write a demand function that we can use to relate the number of units, we'll call that X, of an item that are sold or purchased, or however the models are represented, that consumers are willing to purchase at some particular price. So we have demand functions, we have profit functions, we have cost functions, we have revenue functions. All of those can be differentiated so that we can analyze the rates at which these things are changing. All right, so in this table I put some functions in generic form so that we can familiarize ourselves with some of the variables. So when we're looking at our demand function, this one will always relate price, which we'll use a lowercase p for, and X, which is the number of, or the quantity of items that are sold or purchased, however the functions are written. So you have your price as a function of X. So when you see P and X, and those are the only two variables you see in your equation or your function, that is your demand function. And most of the time you're told that, but it's helpful to just connect the language. Now the cost, I think we understand cost. The cost function, again, is also written in terms of how many items you're producing or selling or are being purchased. So in your cost function, you should see C for cost, and again, X for the quantity or the number of items that we're dealing with. And then when we're dealing with revenue, revenue is the total amount of money that is generated for your company. So the total amount of money that's generated is how many items do you sell multiplied by what is the price of each of those items. So that's what our revenue is. So that's actually three variables in that function. So we have capital R for revenue, and again X for the number of items and P for the price. And then the profit is not the same as revenue. So revenue is the total amount that's generated. The profit is the amount of money that you have remaining from that total after you've subtracted out all of the costs. So for profits, we're going to use the capital P for profits, and again those are going to be found by taking the total amount that's generated and subtracting out all of the costs. So you take all the money you have, pay all your bills, what's left, that's your profit. Okay, so profit again has three variables. The profit function has the revenue and the cost in it. So three variables, and I didn't put that in the description there, but hopefully that makes sense. Okay, so let's look at just a relatively simple example. It might seem a little trivial. It's not really a real world thing, but I mean it sort of is, but it's just not great, okay, but just a basic example. I wanted to show you how all these things sort of tie together, and as we continue to work on derivatives, we will see more of this application. Okay, so for example, we're given the monthly demand and cost functions for X newspapers sold at a newsstand. So based on the demand and cost functions that were given, well, we should be able to come up with the revenue function, and we should also be able to come up with a profit function, and then we should be able to answer questions like, what's the marginal revenue when 500 newspapers are sold? Which means, what is the rate at which that revenue is changing when we sell this many papers? Or what is the rate at which the profits are changing when this many papers are sold? Okay? So let's start in the table. If I want to find marginal revenue, that's the derivative of the revenue because it's the rate of change. If I want to find the marginal profit, that's the derivative of the profit. Well, I don't have those functions yet, so that's why I have to start in this table. Now remember, revenue, we have up here, revenue is the total amount of money that you generate. So that's how many units are you selling times what is the price for each of those units. So up here in our demand function, we're given a function for that price. It says the price is 4 minus negative 0.001 times x. So for revenue, again, I want to take x, number of products that we sell, in this case newspapers that we sell, and multiply by the price. So in this case, the price is, and actually I don't want to skip too many steps here and lose anybody, so let me make this bigger. So our revenue, again, is x times the price. So in this case, x times 4 minus 0.001x, which means our revenue is going to be 4x minus 0.001x squared after we distribute. So there's our revenue function. And then the profit function, again back up here, we can find our profit by taking that revenue, that total amount generated, and subtracting out the cost. And maybe I'll change colors for this one so they're distinct. So again, profit is the total amount generated, the revenue, minus the cost. So in this case, we're going to take our revenue, which is 4x minus 0.001x squared, and subtract out the cost that's given to me up here as 30 plus 1.6x. So we're looking at 4x minus 0.001x squared minus 30 and minus 1.6x. And then finally, we'll put all this in order. So we have this negative 0.001x squared. I can combine 4x and negative 1.6x. So 4 minus 1.6 is going to leave me 2.4x, and then I have that minus 30. So this is my revenue function, and this is my profit function. Okay, so now I have all 4 functions if I needed them. What I'm going to really need are those last 2. So here, find the marginal revenue when 500 newspapers are sold, means find the derivative of that revenue function with respect to x when x equals 500. That's what that's saying. Okay? So if I want to find the derivative of the revenue function with respect to x, I am finding the derivative of the revenue function, which was over there 4x minus 0.001x squared. That's what I'm finding the derivative of. And I can use my power rule twice. So here, if I multiply by my exponent, that's just going to be 4, and that becomes a 0. So that's going to go away. So remember, that's a linear function. My slope will be 4. Minus, multiply here. 0.001 times 2 becomes 0.002 in front of x to the, instead of 2, we subtract 1, and this becomes a 1, which means I don't need that 1 anymore. So there's my derivative. Now if I want to figure out what that is at 500, then I need to plug 500 in. So at 500, we have 4 minus 0.002 times 500, which is going to be something I'm going to put in the calculator so I don't goof this up. So 4 minus 0.002 times 500, and we end up with 3. So we don't have units here, like I don't know if these are dollars or hundreds of dollars or thousands of dollars or whatever, but the rate of change of the revenue with respect to each newspaper that's sold is 3. So we have a positive rate of change for our revenue. Okay? And then we want to, in the next one, find the marginal profit when 500 newspapers are sold. So that is the derivative of the profit function with respect to x. Again, this is when x is equal to 500. So if I want to find the derivative of the profit function with respect to x, then I'm finding the derivative of that thing, that quadratic down there, which was negative 0.001x squared plus 2.4x minus 30. So that derivative is going to equal, let's see, multiply here. So that becomes a negative 0.002 x to the first, because we subtract 1, plus, this is linear, so my slope's just going to be a 2.4, and then the derivative of the constant is going to be 0. So that's my derivative. Now again, I want to figure out what that is at 500, so I'm going to plug that in. So at 500, we're looking at negative 0.002 times 500 plus 2.4, and let me go to my calculator again and cheat a little so I don't have to retype that. And there it is, that's 2.52. There we go, 1.4. So that equals 1.4. That means the rate at which the profit is changing with respect to X when 500 newspapers are sold is 1.4. And again, I don't have any units here, so I don't know if that's like dollars per paper or $1,000 per paper. I don't really know because units weren't given, but that is the rate of change of the profit when 500 newspapers are sold. Okay, so we're going to do a lot more. You'll see as we move on, there'll be some sprinklings of these applications here. But just for now, the keys are when you see that word marginal, that's just rate of change. That's the business or economic term for rate of change. Okay, and these things you don't have to worry about memorizing formulas. Just if you can use them and have these to access, you're going to be totally fine. All right, so I think that's good. I've been dragging on long enough here. If you have any questions, reach out, but I think you should be good to go on your homework. So until next time, take care.